At no point in your rambling, incoherent response were you even close to anything that could be considered a rational thought. Everyone in this room is now dumber for having listened to it.
You lose! Good day, sir!
Hi, welcome to CheMistakes. Here I'm going to go through an actual question that was answered by a student, what the student answered, what they went wrong with, and how you can kind of learn from that so you don't make the same mistake and understand the chemistry a little better. Here we have a thermochemistry problem. We're looking at an enthalpy, and we're looking at a situation for hydrogen peroxide decomposing. We have 7 grams of peroxide decomposing. We're given an enthalpy amount. And then from that, the question is, calculate the amount of heat exchange with the surroundings. Student answer goes through, converts 7 grams into moles, multiplies that by the enthalpy, comes up with 93.6 kilojoules. I want to go through what the student did well, what the student did not understand, and then kind of how to improve this answer a little bit. So the big problem with this, well, let's start with what the student did well. What the student did well was they were clear on what their options were for enthalpy calculations. So they selected the right option. So when you're asked to calculate something along the lines of enthalpy, you can see Hess's law problems, you can see enthalpy of formations, bond enthalpies, and then when you're looking at calorimetry problems, the equation you want to keep in your back pocket is that enthalpy is equivalent to Q per mole. The amount of heat exchange with the surroundings per mole of reaction is equal to your enthalpy change. Now, in that equation, the enthalpy change really is referring to the chemical system, while the Q is often tracked through the surroundings. So this can be a little tricky for new students to kind of have a good, solid understanding of that. What we're looking at is how much energy do the chemicals change by ignoring their thermal energy, and then from that, what does the exchange with the surroundings look like? And so these can be kind of opposing in sign, and that can lead to a lot of misunderstandings for endothermic and exothermic and things like that. So with that said, the student correctly identified that this is the equation they would like to use. They went through and changed into moles of peroxide, and then they used moles times delta H to get the Q. Okay. Now the problem with this equation is that it's not Q per mole of something in particular, and so we need to specify what exactly does this mole mean. And they kind of hint at this in the problem. They say when the equation for hydrogen peroxide decomposing is balanced. So hydrogen peroxide decomposing, H2O2, yields water and oxygen gas. So it probably should be a little clearer, but what they mean by balanced is they mean balanced with whole number integers, so 2, 2, and 1. And that enthalpy then refers to this whole reaction. It's negative 455 kilojoules are released per mole of reaction. What does that mean? That means if 2 moles of this decompose to form 2 moles of this and 1 mole of this, then this is the amount of energy released to the surroundings. So really this is negative 455 kilojoules per 2 moles of this, or per 2 moles of this, or per 1 mole of this. And that can get very tricky, especially if we're looking at situations where you have a limiting and excess reagent. You would want to go with one of the limiting reagent amounts, not the excess. But it's basically giving you a recipe here where we're saying this also releases 455 kilojoules when we follow this recipe. If we don't follow that recipe, we have 0.206 moles. Okay, so the actual answer, what we want to do is we want to take this 0.206 moles of peroxide, and we would want to say for every 2 moles of peroxide, we would expect 455 kilojoules to be released to the surroundings. And so from there, we can see that instead of doing what the student did here, we should be dividing that by 2, and that's going to come out to, I believe, 46.8 kilojoules. Now we want to look at signage. So this is calculate the value of Q. So that's going to be tricky. If we're looking from the perspective of the chemical system, this would be a negative, because the chemicals are going to rearrange, get faster, and then transfer that energy away to the surroundings through collisions. If we're looking from the perspective of the surroundings, rather, this is going to be a positive value. So let's go ahead and put that this is negative from chemical system or positive 46.8 kilojoules for surroundings. So, student here is pretty well along the lines of being able to go ahead and do the equation correctly. They've done all of the math correctly. They just didn't know the per mole, what that referred to. And so that's where this equation comes in handy. It's good to have a written out balanced equation to kind of help you along those lines. And in a situation where you're dealing with multiple amounts, you need to be very cautious with making sure that whatever you use, that you're using something that's a limiting reagent, something that actually is used to completion, even if it's a partial amount. And then you want to make sure that you match that with the coefficient of that particular substance in that equation. To make that even further confusing, there are things such as enthalpy of combustions. And in these, those are per 1 mole of the substance burned. So you might have something like C2H6, and when you balance that, I believe it's 2 C2H6s plus 7 O2s, comes out to 4 CO2s, and what, 6 waters? So for the enthalpy of combustion as reported, it would actually be for half of this reaction. It would be 1 of these plus 3.5 of these, makes 2 of these and 3 of these. They would report that on a per mole of that particular substance basis, which is not the case in a typical reaction like this.
Okay, a simple wrong would have done just fine, but